Can you all hear me?
Yes.
Okay. So, good morning, everyone. I want to talk on the sustainable. Why is it moving? Okay. Sustainable water reuse of biologically treated wastewater. I will be presenting our case studies in a water reclamation plant in Sydney. I will be talking of the membrane-based application, especially the use of dual membrane in high-quality water reuse. The first one, I will be discussing on the combination of nanofiltration and reverse osmosis membrane to remove the organics, pharmaceuticals and personal care products, and some of the divalent and monovalent inorganic ions. First of all, there are many water reclamation plants in Sydney. The largest one, as you could see here, this is the largest one, which has a capacity of 60,000 tons per day. The biologically treated wastewater after the treatment from the 3 inland treatment plants, namely Penrith, St. Mary's and Quakers Hill, are collected in a balanced tank in the advanced water treatment facility, and then they undergo the ultrafiltration and reverse osmosis, and 90% of the biologically treated water can be recycled back to the Nepean Hawkesbury River. The advantage of this is this Nepean River is used for a number of purposes, mainly agriculture, and also it is used as the raw water for a water treatment plant in Richmond. Prior to 2011, the water was not sufficient, so they had to take an environmental flow from the Warragamba Dam. But after this water recycle plant was built, there was no need for the water coming from the Warragamba Dam. And there are many small treatment plants. I will highlight only one, the one in Sydney Olympic Park water reclamation plant, which has a capacity only about 5,000 cubic meter per day or 5,000 tons per day. Here, they use the biological treatment. They use mainly the sequencing batch reactor, followed by the microfiltration and the reverse osmosis. And the water is used for the non-potable purposes in the nearby areas. During the Olympics alone, about 50% of the water was given to the athlete villages and the facilities by this water reclamation plant. The option 1, as I mentioned, which is the combination of the nanofiltration and the reverse osmosis. The reclaimed water here is used for irrigation, and it is an irrigation and non-potable purposes, which is found to be an economical solution. This is because the wastewater has a significant amount of nutrients and which reduce the fertilizer usage. However, we have problems of the excessive salts such as sodium, boron, chloride, nitrate, and so on, and they cause the environmental risk. The excessive salts are measured in terms of the sodium adsorption ratio. I'll come to that one later on. When we have excess sodium ion, it adversely impacts the infiltration of the soil. So it creates issues. And chloride, borate, nitrate at excessive level can damage the plant growth. In addition to that, when we have the pharmaceutical and personal care products, it can lead to contaminated groundwater, which can give the problems to the plants. It can affect the plant growth and give toxicity, as well as the water cannot be used for the potable purposes. So we have to remove the sodium and chloride to a certain level, and the pharmaceutical and personal care products. The sodium, as I mentioned, it reduces the infiltration through the soil profile. The regulations says the sodium adsorption ratio, which is the sodium divided by the calcium and magnesium, should be less than 2 to 8 for the sensitive crops. Chloride should be less than 175 milligram per liter. Sodium should be 115. Boron should be less than 0.5. And pharmaceuticals, if it is found in larger quantities, it can lead to damage to the crop tissues by getting accumulated in the crop tissues. And it can also cause the groundwater or the surface water contamination. This is the characteristics of the feed water after the biological treatment in Olympic Park treatment plant. This biologically treated sewage effluent, which had a very high sodium adsorption ratio of 39, and sodium occasionally is high, more than 120. Chloride is also high. So this the water not suitable for the sensitive crop irrigation, and this is the reason why you need a further treatment. So this treatment plant, as I mentioned, after the secondary treatment and biological treatment of sequencing batch reactor, it goes through the microfiltration, mainly to remove the pathogens and also the remaining solids, and it goes in the plant, it goes through the reverse osmosis, two-stage reverse osmosis. But here what we have done is we used nanofiltration as the first stage and the reverse osmosis as the second stage. We used a number of nanofiltration membranes. Here I am deliberately presenting the large pore size nanofilter, which had only an average quality. Even that one would able to remove about 97% of the organics. However, it could not remove to the expected level of sodium and chloride. So we need, on the other hand, the reverse osmosis removed most of the inorganic compounds in addition to the organic compounds. In terms of the pharmaceutical and personal care products, including the micropollutants, microorganic pollutants, you could see both the nanofiltration and the reverse osmosis removed a majority of the pharmaceuticals. The nanofiltration through the hydrophobic adsorption, it removed about 7 important pharmaceuticals, although the molecular weight cutoff size was higher than 700 Daltons. This is because of the high zeta potential of the membrane. So the membrane had the charge. So some of the pharmaceuticals were removed by the size exclusion and the remaining removed by the charge attraction and repulsion. So the results were nanofiltration still had a sodium adsorption ratio of 14, whereas the safety level is only 8. Chloride slightly higher, sodium slightly higher. These made this is not suitable for the sensitive crops. For the normal crops is okay, but very sensitive crops, they are not okay. But on the other hand, the reverse osmosis permeate satisfied all these parameters. However, it removed also the beneficial ions such as calcium and magnesium, and it had a higher operating cost and underwent the frequent fouling issues. So if we can blend the nanofiltration permeate and allow only the 50% of the water coming out from the nanofilter through the reverse osmosis and then blend them, the sodium adsorption ratio was consistently less than 8, and the chloride and sodium also were removed. So this overcame the soil infiltration problems, toxicity issues by chloride and sodium, and this is cost effective compared to the reverse osmosis alone, and it also satisfied the pharmaceutical removal required. So in this particular case, we found out a blending of the NF and RO effluent at the ratio of 1:1 is good and recommended. There is another advantage. When we use the reverse nanofilter as the pre-treatment to reverse osmosis, or as the first stage to the reverse osmosis, as you could see, the organic fouling was hugely reduced on the RO membranes, which reduced the RO membrane fouling, which reduced the energy requirement. So, and also less energy. The second option, which is the which is the integrated microfiltration activated carbon. The microfiltration is already there in the system, in the treatment plant. We added granular activated carbon. In fact, in our system, the granular activated carbon functioned partially as the biosorbent. So there was no need to remove or regenerate a significant quantity of the GAC. So we used 5% or 2% recycle, by which we can reduce the cost of the GAC. And the GAC amount worked out to be only about 0.2 cents, Australian cent, which will be around only 1 Indian rupee per every every ton of water produced. Then we had the nanofiltration as the second post-treatment, by which we could reduce the amount of the energy without using the reverse osmosis. So this is the system we used in the Sydney Olympic Park system. So here, as I said, the granular activated carbon, which was floating, which also reduced the fouling on the microfilter by mechanical shearing action, and then it reduced the biofouling because the organics, low molecular weight organics, were removed by the first step. We tend to use here the low pressure, which was sufficient in our case. So here, as you could see at the last table, the dissolved organic carbon, there was a removal of more than 94%, and more than 98% of the humics were removed, and low molecular weight organics, which are the main component which lead to the organic fouling in the RO membrane or nanofilter membrane, which are also removed significantly. So we measured the pharmaceutical and personal care products by the dual membrane system. Here we used the granular activated carbon. We only recycle about 10%, or in some cases we recycled about 2% to reduce the cost, and it was coupled with the microfiltration. And as you could see, this is the concentration of the biologically treated sewage effluent, the blue color, and the red color is after the GAC. You can see majority of the micropollutants were removed by this, and then the remaining ones were removed by the nanofiltration, as shown by the green color. So usage of a granular activated carbon microfiltration hybrid system followed by the nanofiltration not only removed the organics, removed all the other pollutants necessary, and also it can be used for the agriculture and non-potable purposes. So these were the ones which were removed by the microfiltration granular activated carbon system to the level less than 5 to 10 nanograms per liter, and the nanofilter removed the remaining 6 of them by the size exclusion and charge repulsion mechanism. The only ones which we could not remove below, which is not significant, which was the caffeine and the carbamazepine. But they also were removed below the standard stipulated. As I mentioned, the use of granular activated carbon prior to nanofilter also reduced the fouling and protected the nanofiltration, and also it also reduced the necessity of cleaning of the microfiltration. So conclusion of the option 1, the treated water, biologically treated sewage effluent, it can be used for the irrigation, and in our case, blending of 50 to 50, 1:1 was sufficient, and it is suitable for irrigation. But the option 2 is more attractive. The blending ratio of nanofilter and reverse osmosis ratio vary with the soil type, the plant which we are growing, and the amount of the salt in the water. On the other hand, the option 2, the dual membrane hybrid system, is capable of removing all the pollutants and mainly the foulants, and the fouling of the microfiltration and nanofiltration can be overcome by the use of granular activated carbon. At the same time, it removes significant amount of the pharmaceuticals and the personal care products, including the other microorganic pollutants. Majority of the PPCPs were less than 5 nanogram per liter, and it also removed the calcium and magnesium and sulfate. And when we use the another nanofilter membrane, NF90, which is a commercial membrane, which could be able to remove even the sodium and chloride a significant amount. Thus, the microfiltration GAC hybrid system with nanofiltration can be used instead of the reverse osmosis economically. And if you don't have the problem of monovalent ions, but the monovalent ions also were removed by some of the nanofiltration membranes known as NF90. So this particular project was funded by the Cooperative Research Center, CRC, and the EU project, Water Harmony project, and the University of New South Wales. They helped us to measure, analyze the pharmaceutical, because we wanted to make sure the values are standard and it doesn't change from laboratory to laboratory. And thanks to Andre, who gave a lot of technical help and who is a manager of the Sydney Olympic Park Authority, provided the facility to do the pilot scale studies and also allowed to collect the water samples for the experiments. Thank you so much.